All solar cells have the same basic job: convert solar energy into electricity as efficiently and reliably as possible. Traditional solar cells are manufactured by exposing very thin wafers of treated crystalline silicon to various chemical and thermal processes, and then applying an anti-reflective coating to the front of the cell. When particles of light, photons, hit the solar cell, energy is transferred to electrons in the silicon cell, allowing them to move about freely. A pathway must then be created to an external circuit so that electrons can be delivered as electricity to power things like lights and household appliances. On a conventional cell, this is done by printing a grid of silver wires called fingers on the cell front that are then interconnected by 2 to 3 thicker pads known as busbars. In order to form an electrical contact between the fingers and the treated silicon material, the cells must be heated or fired to over 800 degrees Celsius. This traditional method creates 3 major challenges. One is that the thick fingers and busbars typical of conventional solar cells increase the amount of shade on the cell's surface, reducing the amount of light collected and converted into energy. 2. Copper wires, called ribbons, that conduct electrical current from cell to cell must be soldered to the busbars. This process can create cell breakage due to high soldering or welding temperatures and mechanical stress. And 3. Traditional solar cells make extensive use of silver particulates within their fingers and busbars, reducing their efficiency. Our technology is different, more advanced, and the result is more energy. It's in our DNA. Let's take a closer look. To begin with, we've changed the busbar architecture. We eliminated those thick, inefficient busbars made of silver paste. We've also eliminated the need for high-temperature soldering by connecting our cells with many electrically efficient copper wires coated with a custom-made low-melting point alloy. These special wires are partially embedded into a thin layer of adhesive that is placed onto a polymeric film with one external busbar along the end. Next, the layers are laminated and vacuum sandwiched together at a low temperature. This reduces the potential brittleness of the cell. With many wires replacing the 2 busbars, the transportation of electrons to a highly conductive contact is achieved more effectively with less resistance and heat generation. And with fewer silver particulates, greater harvesting and lower light conditions is possible when the intensity of energy from the sun is reduced. Finally, the matrix effect of our Stay Powerful technology creates at least 18 times more interconnection points than a standard cell. So if a microcrack normally associated with the traditional busbar architecture does occur, the electron flow is not interrupted. Most photovoltaic or PV modules perform well under ideal conditions. Unfortunately, real-world environments are rarely perfect. Shade from trees and buildings, or the accumulation of snow, leaves, dirt, or even bird droppings can significantly reduce the performance of PV modules. Traditional solar modules utilize conventional busbar architecture. The result is that most solar PV modules comprise just 3 independent zones. This traditional design can result in substantial power output loss due to the effects of shading, debris, and other factors. When a cell is partially shaded, the current flow through the cell is interrupted, disabling the entire zone. And when snow or moss gather across the bottom of a portrait-installed module, all zones are disabled, and the solar module generates virtually no power. Our technology is different, more advanced, and the result is more energy. It's in our DNA. Let's take a closer look. WorkSmart Energy leverages the unique design of our Stay Powerful technology, replacing the rigid busbar design with a matrix of specially coated copper wires with just one external busbar along the end. This results in greater flexibility in how the cells are configured and interconnected, allowing for many more independent operating zones, up to 3 times that of a traditional module. When a single cell is obstructed, a traditional PV module produces about 65% of its maximum output. On a solar module with WorkSmart technology, however, an equivalent obstruction has a much smaller impact. Module output is maintained at between 85 and 90%. And in a case where approximately 10 to 18 centimeters of the bottom of the module is covered by accumulating debris such as snow or moss, a WorkSmart-equipped module would still achieve 90% power output, where the traditional module would fail to generate any power at all. WorkSmart technology delivers a higher energy yield for various types of projects. For a typical residential or commercial rooftop installation, the accumulation of leaves or snow and time of day shading from chimneys, trees, or other buildings can significantly reduce the amount of electricity generated. With WorkSmart equipped solar modules, PV installations produce more electricity even under the most challenging conditions, and annual energy yields may increase by 20% with just 1 additional hour per day of energy harvest. For larger, fixed, ground-based systems, installations are typically designed to prevent modules from casting shadows on subsequent rows when the sun is lower in the winter sky. WorkSmart technology allows for a higher module density, producing up to 25% greater annual power from the same project area, an important consideration with a high cost of land. And finally, because solar modules equipped with WorkSmart technology are designed to perform optimally when installed in portrait mode, installation costs are dramatically lower. Due to the reduced length of module rows, portrait installation requires up to 60% less racking, mounting, and installation materials than a landscape-oriented installation. Solar photovoltaic, or PV, modules perform well under ideal conditions and during their initial years of installation. Unfortunately, challenging environmental conditions over 25 years of operation may significantly affect the performance of conventionally built modules. Choosing a quality solar PV system that is optimized for year-in, year-out service is critical to maximizing the value of your energy investment over the long term. Most modules, when exposed to the thermal stress of daily heating and cooling, can develop cell breakage and microcracks which significantly reduce energy production. Challenging environmental conditions, such as moisture, extremes in temperature, salt mist, and harmful gases from farms and greenhouses, can further reduce energy yield. Day-to-day reliability and long-term durability of PV modules may be further compromised by the use of inexpensive, lower-quality components found in some solar modules. To begin with, we changed the traditional busbar architecture. Powerful technology connects solar cells with many electrically efficient copper wires coated with a custom-made, low melting point alloy. These special wires are partially embedded into a thin layer of adhesive that is placed into a polymeric film with one external busbar along the end. This innovative design provides greater durability and reduces cell brittleness compared to traditional solder-based cells. Stay Powerful technology also creates at least 18 times more interconnection points than a standard cell, so if a microcrack normally associated with a traditional busbar architecture does occur, the electron flow is not interrupted. Secondly, modules with the live-long mark feature quality encapsulation material and a unique multi-layer backsheet material with aluminum foil. Certified to protect from the damaging effects of moisture and salt mist, these solar modules are also immune to the damaging effects of ammonia from greenhouses and farmlands. Advanced technologies and materials also result in superior performance in hot climates. The copper wires of Stay Powerful technology act as a heat sink, and the aluminum layer in the backsheet wicks away added heat. A lower operating temperature means better efficiency and more electricity. The result is modules with one of the lowest certified nominal operating cell temperatures in the industry, with an operating temperature that is 3 degrees Celsius lower on average. These technologically advanced modules enjoy a 1.5% efficiency advantage over generic modules, which can result in significantly more electricity over the lifetime of an installation.